Dear students, this is a continuation of the lecture series on the topic Laplace transform. In our previous video, we learnt problems on the first shifting theorem. So after completing the problems on first shifting theorem, now here we move on to the next theorem, which says that the Laplace transform of f of t is equal to f of s. So if we have this, then the Laplace transform of t f of t, that is the function t, when it is multiplied with t, we get it to be negative d by ds of f of s. So when we differentiate this with respect to s and multiply by negative 1, we get the result for Laplace transform of t f of t. So now let us prove this theorem, and further we will solve problems using this theorem. So in order to prove this theorem, we shall first consider the given part. That is, it is given that L of f of t is equal to capital F of s. So we can rewrite this as capital F of s is equal to L of f of t. Now we shall differentiate on both the sides with respect to s. So differentiating on both the sides with respect to s. So we get d by ds of capital F of s is equal to, so we differentiate with respect to s, and so we get d by ds of capital F of s to be equal to d by ds of Laplace transform of f of t. Now further, we shall substitute the Laplace transform from the definition over here. So by the definition of Laplace transform, we know that L of f of t is equal to integral 0 to infinity e to the power negative st f of t dt. Already I have given the definition for Laplace transform, so you can see from that and you can write this. So we have written the definition of Laplace transform of f of t. Now we want to take this differentiation within the integral. But if we see within the integral, there are two variables, that is already we have to differentiate with respect to s, and the other variable is t. So we have s and t. So because of that, and this differentiation is only with respect to s, when it goes into the integral, it becomes a partial derivative with respect to s. So dou by dou s of, so integral 0 to infinity dou by dou s of e to the power negative st f of t dt. Now we shall differentiate this with respect to s. So we have s only over here. So we have to differentiate only e to the power negative st with respect to s. So when we differentiate, we get it to be integral 0 to infinity, and the differentiation of e to the power negative st is same, e to the power negative st, and we have to multiply with the constant. So here if you see, we are differentiating with respect to s, so t will be treated as constant, so it will be multiplied by negative t multiplied by f of t dt. Now we can take this negative sign outside the integral. So negative integral 0 to infinity, and this can be written as e to the power negative st multiplied with, we can combine these two functions and we can write t f of t dt. So from the definition of Laplace transform, we observe that this is equal to, so we negative, so this whole integral will be equal to Laplace transform of, now here the function is t f of t, so t f of t. So from the definition of Laplace transform, we have written this. So on the left we have d by ds of capital F of s. So this can be rewritten now. So L of f of t, so L of t f of t will be equal to, so negative can be taken to the other side, so negative d by ds of capital F of s. So hence we have proved the theorem. You can see that we have proved the required result, and therefore the theorem is proved. Now we will see the corollary of this theorem. So before seeing the corollary, we can just rewrite this theorem. That is, we know that L of t f of t is equal to negative d by ds of f of s. But what is f of s? It is L of f of t. So we will just rewrite this result. So we have to use this result in the form L of t f of t. So while solving the problems, we have to use the result in this form. So is equal to negative d by ds of, we will replace capital F of s. So it will be a d by ds of L of f of t. So this is how we will be using in the problems also. Now we will see the corollaries. So the first corollary will be, so if you see previously we have found L of t f of t. So from using this we have to find L of t square f of t. Now this can be rewritten as L of t multiplied with t f of t. So now here the function becomes t f of t. So we will apply this. So we have t, and instead of f of t we have t f of t. So wherever we have f of t, we have to replace it by t f of t. And so this will be equal to, so using this we will be having negative d by ds of L of, now instead of f of t what we have here, t f of t. So t f of t. But again we have to replace this Laplace transform of t f of t by negative d by ds of L of f of t. So this will be further equal to negative d by ds of, now using this we will be having negative d by ds of L of f of t. So combining this now, this negative 1 and negative 1 gets multiplied and we can write it as negative 1 square, and this will be d square by ds square of L of f of t. So this is the required result. So therefore L of t square f of t will be equal to negative 1 square d square by ds square of L of f of t. Using in a similar way, we can find L of t cube f of t, which will be equal to negative 1 the whole cube d cube by ds cube of L of f of t. So this is another one. In general, if we have t to the power n, so L of t to the power n f of t will be equal to negative 1 to the power n d power n by ds power n of L of f of t. So this is the general one. So therefore these are the corollaries which we will be using while solving the problems on this topic. So this is the main result. Using this result, we have obtained these corollaries. So in our next video, we will solve problems using this theorem. Thank you.